All right, so last speaker of the session is Silvia Arjona Garcia, and she will talk about comparing the stellar environment of hot and warm Jupiters, a neural network analysis of Gaia spectrophotometry.
Hello. Okay. Thank you. Oh, just this. Oh, okay, cool. Hi, everyone. My name is Silvia Arjona Garcia. I'm an astrophysics and computer science student at the University of Hawaii at Manoa. And today I'm going to talk to you about the project that I spent my summer working on at Gemini Observatory with Cicero Liu and Winston Wu, titled Comparing the Stellar Environments of Hot and Warm Jupiters, a Neural Network Analysis of Gaia Spectrophotometry. So, I'm not going to go too deep into what hot and warm Jupiters are, since most people have already talked about that. But I'm going to mention the three sort of host star properties that I looked at to use as a proxy during my project. The first one being metallicity. And so more metals just means that it has more planet-forming materials. I looked at effective temperature, since a hotter star sort of indicates a more massive star and a more massive disk. And finally, surface gravity, since a higher surface gravity correlates to a compact main sequence star, and lower surface gravity correlates to usually an evolved giant. And so of these three, I looked at metallicity the most closely, because there has been a correlation between abundance in stars that host exoplanets and metallicity for a much longer time than the other two. So that's just sort of what I focused the most on in my project. And so this is the question that sort of guided me throughout the summer, which was, do hot and warm Jupiter samples form in different environments, and can we see those differences through the metallicity distributions of their host stars? So I just use this to actually focus my project on answering this question. And this is how my project flowed throughout the summer, sort of the steps I took to actually answer this question. I started by creating 4 different samples of warm and hot Jupiters to actually apply my models to at the end. After that, I built 2 different neural networks, trained them on a data set using Gaia data. And once I had those not perfected, but in the best possible state models, I actually did apply those to the 4 initial samples, and then pulled results from that, tried to see what patterns I could recognize, and went from there. So now, where is this data that I mentioned coming from? So the actual training data set that I use to train and evaluate and just repeat that process with my models comes from Gaia. I use both RVS spectra and XP spectra, since together they sort of, each one makes up for what the other lacks. And then for the actual data set that I applied my models to at the end, I started with data from tests using NASA's exoplanet archive. I filtered it by temperature and radius, and then by high and low eccentricity. So for warm Jupiters, a sample with high and low eccentricity, and the same for hot Jupiters, for a total of 4 samples. And then once I had those samples, I cross-matched them with Gaia, so that each host star had its respective Gaia DR3 ID, which just made filtering, processing, everything so much easier in my models. And then, so actually getting into what my 2 models are, I started with a feed-forward neural network, or FFNN. This is the simplest type of neural network that can be made. It has 3 to 4 fully connected layers, and it flattens flux values, which basically means it just takes the flux from the spectra as a single input, sort of disregarding each value individually and just looking at it as one value. And this just makes it a much more simpler baseline model, and does a good job of looking at global patterns, but not very specific small patterns in the spectra. And then once I had that at the level I wanted it, I used it as a base to make a convolutional neural network, or CNN, which includes convolutional layers and pooling layers. And this preserves wavelength ordering. So rather than taking flux as one big value, it actually looks at each flux value independently, along with its respective wavelength value. And this just makes it a lot more complex, and it does a much better job of learning those specific spectral line patterns and picking up more of those underlying patterns in the spectra. And so here are 3 different sort of problems that I encountered throughout this project that also sort of shaped how my models worked. The first one being that the Gaia data set that I actually trained and tested my models on is massive. It had almost 1 million different stars. And if I just tried to run my models on that data just like that, it would probably crash the system, which unfortunately did happen several times. And to sort of deal with that, I used chunked pre-processing and dynamic chunk size, which basically just means that it loads the data from that data set in chunks, and the system looks at how much RAM is available in the GPU at that time, and depending on that availability, it determines the size of the chunks. Next, in this data set, not all of the stars have XP and RVS spectra. Some have one, some have the other, some have both. And so my models needed to be able to deal with that difference. And to do that, I used binary masking for the XP and RVS per sample, and then combine them by averaging. So if the sample had just XP, it just used the XP one. If it had just the RVS spectra, it used that one. If it had both, it averaged them. So it could deal with all three scenarios, no problem. And finally, I had to deal with the fact that XP and RVS spectra have different wavelength sampling. They work across two very different ranges of wavelengths. And to deal with that, I just normalized them onto a shared wavelength scale and included the wavelength information as part of the input into the model, not just the flux. So actually getting into how my models performed, overall, the convolutional neural network did a better job, which makes sense since it is a bit more complex. And then I used a system called TensorBoard. As you can see in the graphs on the right, it's basically just a graph of how mean absolute error is changing as the model is training and evaluating and testing. And as you can see, the convolutional neural network sort of decreased to a lower value, which is good. But at the end, it started going back up, which is just something called overfitting, which tends to happen with CNNs because since they are more complex and pick up more of those really minute details, sometimes they can start just memorizing the patterns rather than actually using them to predict new values. But that wasn't really a huge issue. And then another visualization that I used to determine how accurate my models were these actual versus predicted scatter plots, which are exactly what they sound like. It's just the actual values from the data set compared to my predicted values for my models. So ideally, if the models were just perfect, they would all lie across that one-to-one line. Of course, they're not. But as you can see, comparing one of my initial models versus the last one, the difference is pretty significant in how clean and sort of squished to that line that data is. So this was just a visual comparison that made it easy for me to see immediately how well the models were performing. And then I actually used my models on some Kepler objects of interest from a 2016 paper to test my models on sort of external values that weren't just the samples that I created. And as you can see, compared to just two baseline models and my feedforward and convolutional neural network, mine performed marginally better. Specifically, the CNN, it's not a huge difference, but it's there. And you can see that the CNN did perform just slightly better than the feed-forward one, which is what I like to see. Then getting into the actual results that I pulled from this, here are the metallicity distributions of hot and warm Jupiters. And as you can see, on average, the warm Jupiters seem to have a higher metallicity, but more specifically, they have a wider distribution of values, which is very interesting. And this difference in the distribution suggests that discomposition shapes where these giant planets end up, or sort of like their migration history, which is very cool to see. But more interestingly, if I show you the metallicity distributions in terms of high and low eccentricity, as in those 4 samples that I mentioned at the beginning, for hot Jupiters, there isn't a huge difference, or there isn't actually a difference at all in that average metallicity, as you can see. But for warm Jupiters, there is a difference in that average metallicity across the high and low eccentricity samples. And so this just suggests that higher metallicity can favor eccentric and dynamically active systems. So this could lead to telling us about the conditions in which these systems formed, whether they were more chaotic or if they were less chaotic, and sort of that history, which is what we're trying to find out. So that was a very interesting result. And just to summarize, I built and compared 2 different neural networks, applied to my models to exoplanet host stars, found some surprising trends, and I'm building a web app with one of my mentors that unfortunately you can't see, but it's there. And in the future, I would like to expand to the other stellar properties, not just metallicity, maybe use some Gemini observed data since I did have the opportunity to work there this summer. And then, like I said, making this a public tool. So if you have the ID for a star from Gaia, you could just plug it into my model and get those predictions instantly, which is really cool. And then I do have 2 papers in progress that I'm working on with my mentors. Thank you.
Great talk. Questions? Okay, we have one in the back. Yeah.
Hi, great talk. Zerka Herman, NASA Ames. So for your model, when you go through the Gaia data and select the Gaia data, do you make any cuts to remove unresolved binaries?
To remove what? Sorry?
Unresolved binaries.
I'm so sorry. I'm not sure what that is.
Okay.
Actually, I can answer that question for you. No, we did not look at the binary fraction. So maybe this is something, a next step we can look at. So could be something interesting to discuss offline. Yeah.
Any other questions? Go ahead.
I have a question. Yeah, this is really cool work. There was some structure in your actual versus predicted parameter spaces. Do you know why you're getting the kind of strong structures?
Yeah, so sometimes the models, like I mentioned, the overfitting, sometimes the models start to just memorize the patterns rather than actually predict them, which just happens with any sort of machine learning. Sometimes they do just start to memorize them rather than actually give new values. So that's where those structures come from. And to fix that, I just used more layers within my models, just made them more deep is the word. So yeah.
Yeah, and then I want to comment on that comment as well. The other reason for the structure is that because in the first place, the naive model doesn't consider the wavelength ranges, so it actually treats XP and RVS with that just with the flux spaces without looking at the respective effective wavelength range. When Silvia incorporated the relative scaling of the wavelength ranges in her normalization, that problem also sort of goes away. Yeah.
All right, great. Let's thank Silvia again. And let's thank all speakers in this morning session for these great talks.